as a next step, we want to talk about how we can describe subsets of projective space as cut out by some kind of polynomial equations. Because the big picture is the affine varieties were defined as the solution sets of polynomial equations in the coordinates given on AN. So for example, we had things like the vanishing locus of x1 squared minus x2 inside A2. That's a very nice affine variety. However, for projective space, we can't do exactly the same thing with the homogeneous coordinates that we saw. And the problem is, like, how would we define this vanishing locus here, given by this equation? Well, you could say, well, maybe just, well, write down this equation here. But then you see this equation is not independent of the scaling here. Because, for example, if you take the point 1, 1, 1, then if you plug these coordinates in, then you get 1 squared minus 1 is 0. So that would be in there. On the other hand, this is the same point as the point minus 1, minus 1, minus 1, just scaling everything by the scalar minus 1. And if you plug these coordinates in, you see minus 1 squared minus minus 1. And this gives you 2, which is non-zero, at least if the characteristic of the field is not 2. And so somehow being 0 or non-zero is not independent of which representative you pick here. And so that's a problem. But this problem can be solved if the polynomial equations that you input are given by homogeneous polynomials, which means these are polynomials such that all the monomials which appear in there have the same total degree d. And that's the first observation that we want to do. So if f is a polynomial homogeneous of degree d, then, well, what happens if we do some maneuver like this? So if we scale all of the coordinates by the same lambda, well, in fact, you can also define being homogeneous as saying that multiplying all coordinates by lambda is just the same thing as drawing out one common factor lambda to the d. Because if you have these monomials of total degree d, then you get exactly d factors lambda in there, in all of the monomials, so you can draw it out. In particular, looking at this equation, then this f at the scaled point is 0 if and only if f at the original point was 0, because lambda is assumed to be a non-zero element of K. And so this equivalence tells you that the 0 locus of this homogeneous polynomial is well defined in projective space. And so if we had taken a slightly different polynomial, so for example, this x0 squared minus x0, x1, that's a polynomial in 2 variables, and we look at what is the 0 locus inside P1, then, well, first of all, we can check this equality here. If we scale 2 things by lambda, then we get this, and then you see the first term, you have a single term, but then with a power 2, so you get a lambda squared. And here you can combine these 2 lambdas to a lambda squared, so you get a global factor lambda squared times the polynomial you started with. And so we can see that this condition f being 0 at this point here is well defined. And then to actually calculate it, you can look at this equation and see, well, one can draw out a factor x0, and the remaining factor is an x0 minus x1. And then this polynomial here vanishes if and only if one of the factors vanishes. So in other words, it's the locus of these points where x0 is 0, union the locus where x0 equals x1. And then, I mean, you should get used to these homogeneous coordinates. If x0 is 0, then these are the points 0, comma x1. x1 is non-zero, but then you can scale this second coordinate to be 1 by dividing by x1. And so this is in fact just a single element set containing this point here. And similarly, if x0 equals x1, then these are points of the form x, comma x, and then you can divide by x and you get the point 1, comma 1. Okay. So we see this vanishing set of this polynomial is well defined on P1. And for later use, we want to formulate this a bit more generally. So here we talked about polynomials and what it means for them to be homogeneous, but in fact, you can do this more generally. And this will be necessary when we define things like the coordinate rings of more general projective varieties. So what we should do is we should do it in this more general setting, and this is the setting of graded rings. We'll have a bit of a reminder. In principle, this was part of the commutative algebra lecture, but it's never, doesn't hurt to recall a bit the notation. So definition, a graded ring is, first of all, a ring R together with some abelian subgroups RD inside the group R comma plus for all D. So these are closed under addition. And the D's that we consider are these natural numbers, so 0, 1, 2, and so on. And you require two conditions. One is that R is, as an abelian group, the direct sum over all of these RDs. So in other words, every F inside R has a unique decomposition as a sum of FDs, which sit in these RDs, and only finitely many of those are allowed to be non-zero. That's the definition of this direct sum of groups. And the second condition is, now we have something with the multiplicative structure of R, namely, if you have F in RD and G in RE, then the product F times G is in RD plus E. And then this is the end of the definition. And then when you have a non-zero element inside R, we define its degree to be the maximum of these D such that FD is non-zero. And then the idea, for example, for the second condition is that if you have F of degree D and G of degree E, then their product should be of degree D plus E. And in fact, these elements of RD minus 0, these are then called homogeneous of degree D. And these decompositions which exist, like F can be decomposed in the FDs and R decomposed in the RDs, these are then called the homogeneous decompositions of F and R, respectively. And if R is also a K-algebra, then we say it's a graded K-algebra if, well, lambda times F is in RD when lambda is in K and F is in RD. So in other words, multiplying something in RD with a scalar in K doesn't change the degree. And the main example for us will be the polynomial ring in n plus 1 variables, which we always call x0 up to xn, because this makes a lot of the indices much nicer behaved than going from 1 to n plus 1. And so this polynomial ring is a graded K-algebra, and we can give these RDs, namely R0, is just K, is just a constant polynomials, which you can see as the span of just the constant polynomial 1. Then R1, these are the homogeneous elements of degree 1. And this is just the span of these x0 up to xn, so the linear polynomials. And R2, then degree 2 polynomials. So homogeneous of degree 2 means that you are a linear combination of all of these monomials of degree 2. And in general, RD is then linear combinations of these monomials here, such that the sum of the exponents is equal to D. Okay. And then the homogeneous decomposition, if you have such an F like this, for example, then you see its degree 0 term, F0 is actually 0. Then F1, the degree 1 term is, well, the sum of all the terms of degree 1. Degree 2 term is this here. Degree 3 is also 0, and degree 4 is the x3 to the 4. So this would be the homogeneous decomposition in this case. And that's kind of nice exercises. So first of all, to check whether you understood all the parts of this definition, you can ask what part of the definition goes wrong if you take the power series ring of formal power series in n variables over k, because that is not a graded ring with the definition above. And then the second thing, if you have R non-equal to 0 graded ring, we can confirm some of our intuitions, namely 1 inside R is homogeneous of degree 0. We kind of expect that 1 should be something like a constant. If you know that, then you can conclude actually this grading on this polynomial ring above. We defined it by giving these very explicit conditions, but in fact, the claim is it's uniquely determined by just saying that x0 up to xn are all homogeneous of degree 1. So think about how you can show this using this assumption. And more general, there's other gradings on this polynomial ring. So you could declare that xi has degree di for any tuple of numbers di in the natural numbers. Okay. And so next we're going to talk about ideals in these graded rings, and in particular ideals which play nicely with respect to the grading.